Hello and welcome back to math class in session. Today we'll graph transformations of our most recent parent function y equals b to the x. So we'll graph transformations of y equals b to the x. Example: describe the transformations to be applied to y equals 2 to the x in order to graph a transformed function y equals negative 2 to the x plus 3 subtract 5. Solution: recall our basic formula. Y equals a multiple, or a times f of b times x minus d plus c. And these variables, a, b, d, and c, note that f is not a variable because it is a set of ordered pairs. It's a function. But the variables a, b, d, and c each affected that set of ordered pairs in their own special way. For example, a multiplied the y values, and if negative, reflected in the x-axis, and usually was a vertical stretch. B divided the x values, usually was a horizontal compression. D, if you saw subtraction here, would shift the entire graph to the right, while C, if you saw a plus sign, would shift the graph up. From this idea, we can get a list of transformations. For this transformed function, the transformations are, now we shall make a list and read from left to right. Now the first thing I encounter that's different from y equals 2 to the x, the first thing I encounter that's different from that is a subtraction. So that's our first transformation. It's a negative a value, which is a reflection in the x-axis. The next thing I encounter that is different from the parent function is x plus 3. And since that's in brackets with the x, even though there's no brackets necessary, it's close with the x, it will be a shift to the right. Wait a minute, it's a shift to the right when there's a subtraction, so this is shift to the left 3 units. And the subtract 5 here on the end is a negative c value. So instead of shifting up, it shifts down 5 units. And that's a list of the transformations. Let's do it again. Describe the transformations to be applied to a given function in order to graph that same function transformed. Let's make a list. Solution: we notice the need to rewrite the function because in the standard equation it's a single x, and that's not 1x, that's 3x. So we need to make sure there's a single x in the brackets. We common factor out the 3. Here it comes out nicely. Even if it didn't come out nicely, it's still necessary to factor out or divide out 3. And now we can simply read left to right. The transformations are, I see an a value of 5, so that's a vertical stretch, factor 5. I see a b value of 3, so we'll horizontally compress by a factor of 3, or 1/3. I see a subtract 2, so that's a shift to the right, and then I see a c value here of plus 2, so shift right 2 and up 2. Let's do a third example. State the equation of the asymptote, the y-intercept, and the range of the function and sketch. And here's a transformed function. It looks like y equals a quarter to the x with a couple of transformations involved. Solution: for the asymptote, we see that this function, that the function 1/4 to the x, has been shifted down 2 units. So we have to analyze it a bit and understand the entire graph has been shifted down 2 units. So the asymptote, which was normally at y equals 0, has been shifted down to y equals negative 2, the new asymptote. Now I stress here, this number on the end is always the asymptote for exponential functions. So if you're asked what is the asymptote of the following, There it is there. It's y equals -2. We know that the parent function exists above this asymptote. It's the plane landing. So the range of this function must be all the y values that are above that asymptote, because the function exists above the asymptote and is approaching it from the above, and so the range of the function is everything above -2. Y is greater than -2. The y-intercept is next. To find a y-intercept of any function at any point in time in your education, if you would like a y-intercept, sub in 0 for x. Because at a y-intercept, x is 0. So if we were to plug in 0 here for x, we can see that this 1/4 to the 0 would be 1, and this would be 4 times 1, which is 4, and 4 subtract 2 is 2. So the y-intercept is then 2 when we sub in 0 for x. Doing the math here, writing it out, 4 times 1/4 to the 0, which is 4 times 1, which is 4. Subtract this 2, and we have 2. And that's how we can find the y-intercept is 0, 2. And now, next, it says sketch. So here's our function. There's our asymptote. There's our range. There's our y-intercept. Let's put it all on a grid. Here's a grid. Here's what we are attempting to graph. And there's our y-intercept. Here's our y-axis, so we can put our y-intercept on it, which we figured out to be 2. Now we know that this is the plane landing. It's 1/4 to the exponent x, so it's shaped like it's decreasing. It's a decreasing exponential function coming down through this y-intercept and landing on its asymptote, getting closer and closer to its asymptote, which we know to be y equals -2. So on our sketch, we can put an asymptote here on y equals -2, because we know that this is where this graph is going. Next, we'll need these things called lattice points, specific points, to show us where the function is. It could be coming from not very high and gently coming through the y-intercept and then gently approaching this asymptote, or it might be plunging down steeply, coming down to touch it quickly, but never quite actually getting there. Let's find out just where this function is by finding more points, and the more points are called lattice points. So if I subbed in 1 for x, we have 1/4 times 4, and that's 1, and 1 minus 2 is -1. So it must go through 1, -1, right there. Let's sub in -1 for x. Now 1/4 to the -1, well, we know that's the number 4. 4 times 4 is 16, and 16 subtract 2 is 14. So at -1, this graph must be going through 14. Now we know exactly where this graph goes. It plunges down through those lattice points, through that y-intercept, and approaches the asymptote. And the software tells us that's it. Label your graph, and that's how you sketch an exponential function. Asymptotes, y-intercepts, and a couple of lattice points. Let's do it again. Sketch this function, y equals 2 times 3 to the x subtract 5. We'll need a y-intercept, which we get by substituting 0 for x. This will be 2 times 1 is 2, subtract 5, -3. And now let's put that on our graph. 0 minus 3, go to 0 minus 3. We need to know how to plot points. Next, we can work on our asymptote here. The asymptote we know is this number on the end, y equals -5. And because the base is bigger than 1, we know that this one will be shaped like the population of the Earth, so the asymptote will be on the left-hand side this time. As opposed to the previous one when the asymptote was on the right-hand side, this asymptote will be on the left-hand side along this line here, y equals -5. Put that on. And next, we would like very much to have a lattice point. So we can sub in numbers for x and get specific exact numbers. If I subbed in 1 for x, it would be 2 times 3 is 6, minus 5 is also 1. So it should go through 1, 1, right there. And now we know that this graph is taking off asymptotic to this asymptote up through this y-intercept and taking off sharply, steeply up through that lattice point and on and up like that. Don't forget to label your graph. Let's sketch another one. We see here that this is a decreasing function, kind of like the plane landing, because the base of the exponential function is less than 1. So it will be a decreasing function which has been reflected across the x-axis. So if you use your imagination, if something is decreasing and you reflect it across the x-axis, all of a sudden it's climbing upwards. And it's been shifted down too. So we know where our asymptote is. It's at -2. Y equals -2. The y-intercept is 0, 3, because if you put in a 0 for x here, we have -1, subtract 2, which is -3. So we can put that on our graph, 0, -3. We know the asymptote is at y equals -2. It's always the number on the end, so we can put that y equals -2, and it will be on the right, because this is the decreasing function reflected, so it will be on the right there. And we need a lattice point, or 2. Let's try a negative lattice point, like -1. Why? Because a half to the -1 is 2. So if x is -1, this part of the expression is -2, subtract another 2 makes it -4. So a lattice point will be at -1, -4. Here it is here, -1, -4. We can get another lattice point quite easily, because if we subbed in -2 for x, this is inverted and squared. So if we invert this, we got 2, and then square that, we got 4. So -4 subtract 2 is -6. So another lattice point exists at -2, -6. Let's go there, -2. Right there, there will be another lattice point. And what the heck? We might as well get a third lattice point because they're easy to get. So put a -3 in here for x, invert this and cube it, and you have 8, and -8 subtract 2 is -10. So if we plugged in -3 for x, we would go along the x-axis to -3 and go all the way down to -10, and we know that we're going to find yet another lattice point. And we can see the curve is appearing before our very eyes, and all we need to do is join it together with a smooth curve, and don't forget to label it. And this is graphing transformations of exponential functions.